All right, so let's tie all this in together. Let's tie this in together with delta G and K. And K in this case is our equilibrium constant. And we have this way to relate these three together because this tells you about spontaneity. This tells you about the extent of a chemical reaction, and we can relate these two together. And now I can pull in my cell potential for a redox reaction and relate that as well, because I can say something about spontaneity. If this value is positive, I know that that reaction is going to be spontaneous. So all of these are interconnected and related together. So some of these we've already looked at in terms of their relationships, but others we have not. We learned in the last chapter that we can relate these two together using this equation here. Delta G under standard conditions is going to equal to negative RT ln K. And R was 8.314 joules mole Kelvin. And temperature was in Kelvin. And so that relates delta G and KEQ. So we have two new relationships here that deal with this cell potential for a galvanic cell, this guy. So delta G equals negative N, and N is going to be our number of electrons transferred in that redox reaction. F is Faraday's constant, and E cell is what you're going to be calculating based on your half cell potentials. So I can go this route, but I can also relate these two directly to each other using this equation here. My cell potential is equal to 0.0592 volts divided by N. N is the number of moles that are transferred in that redox reaction equals the log of K. And so I have these three equations here that are going to allow me to toggle between equilibrium constant and cell potential for redox and my Gibbs free energy. Faraday's constant is 96. It's a large number. 485, and it has units of coulombs per mole electron. N is always going to be number of moles of electrons transferred. So a couple of things just to keep in mind when this is positive, it's spontaneous. When delta G is negative, it's spontaneous. When my cell is negative, it's non-spontaneous. When delta G is positive, it's non-spontaneous. So a little bit of difference here in my signs. When K equals 1, delta G equals 0. When K is greater than 1, then I'm going to have a spontaneous reaction. When K is less than 1, it's non-spontaneous. So just some things to keep in mind as we're going around through here. So the signs here are going to be different for spontaneous reaction. This is always going to be a positive value, but if it's less than 1, it's non-spontaneous. If it's greater than 1, it's spontaneous, meaning it's favoring the formation of those products. So it's easy to kind of get lost in all that. So let's just do one quick example here. Let's say I have I2 solid, and I react that with a bromine ion, aqueous. So I have solid iodine, and I drop that into a solution of bromine. Is this going to happen? Is there going to be a transfer of electrons here to form liquid bromine and iodide ion? And I want to find delta G for this reaction. I'm going to break this up. This is obviously a redox reaction, so I'm going to assign oxidation numbers here. I'm going to track what's undergoing oxidation and what's undergoing reduction. So this is my reduction half because my oxidation number is going down. That's happening at the cathode. This is going from -1 to 0, so this is going to be my oxidation half. That's happening at the anode. If I calculate E for this, then I can use that to calculate delta G because I know that this relationship here. So I'm going to do this first. I'm going to find these values off of a table. So this is reduction, so my electrons are going to be on the reactant side. It's picking up, I have 2 of these. Each one is picking up 1 electron, so 2 electrons are being transferred. I'll look at my cathode, and I'll look at my anode values, and then I'm going to plug those in. So my cathode is 0.54 volts. My anode is 1.09 volts. This is my iodine here. So this is what's undergoing reduction, 0.54 volts. And then my bromine is higher up. So this is going to be a non-spontaneous reaction because everything that's going to be higher than iodine is going to want to preferentially undergo reduction, and then iodine would be forced to undergo oxidation. So as I have this written, I'm already predicting that this is going to be a non-spontaneous reaction because this is higher in value. So E cell is going to be my cathode minus my anode. That's going to give me a negative value, which also tells me that it is non-spontaneous. And then if I want to calculate delta G, I'm going to expect a positive value for delta G because delta G would be positive under a non-spontaneous reaction. So when I plug this into my equation here, delta G is going to be equal, N is 2 because 2 electrons are being transferred. I'm going to multiply that by Faraday's constant, and then I'm going to multiply that by negative 0.55 volts out of my paper here. That's going to give me a delta G of 1.1 times 10 to the 5th joules. Because remember, 1 volt is 1 joule per coulomb, so when I plug this in, my volts will actually be joules per coulomb. My coulombs will cancel out, my moles of E will cancel out, and I'll just be left with joules. And then if I wanted to put that into kilojoules, I could do that. I could also find my equilibrium constant for this reaction. I could either plug it into here, or I could get to G and go this direction. So I could also find K from this as well. And I would expect K to be a small value, less than 1, because it's non-spontaneous. All right, let's talk about things that are happening under non-standard conditions. Remember our standard conditions. If I have a gas, that's at 1 atmosphere. If I have an aqueous solution, that's at 1 molar. Everything is in their standard states. I'm at 298 Kelvin is my temperature. These are all my standard conditions. So oftentimes in these voltaic cells, because you're dealing with aqueous solutions, you may not always have 1 molar. And that would be an instance where you would have non-standard conditions. If I have non-standard conditions, I need to use this equation called the Nernst equation. And just like we did with delta G, where we had an equation that related our new delta G to delta G under standard conditions, we're also going to have a new cell potential and relate that to the cell potential under standard conditions. So the Nernst equation looks like this. So here's my cell under standard conditions, and then I'm going to subtract this value here. Volts over N, where N is my moles of electrons that are being transferred, log Q, and Q is my reaction quotient. So that's going to allow me to take these non-standard conditions and plug them into here. That's going to also tell me which direction the reaction is going. So let's say I have zinc solid, and I'm reacting that with copper ion, and I'm going to form zinc ion and solid copper metal. I can calculate my standard E cell potential. This is going to be my oxidation half because this is going up. So this is going to be at the anode. This is my reduction half. This is going to be at the cathode. So I'm going to find that first. I'm going to calculate my E cell potential here. So my anode is zinc here. Zinc solid going to zinc ion. That's a negative 0.76. And then my cathode is copper 2 plus going to solid copper. So I'm going to look specifically for copper 2 plus. So I have copper 2 plus going to copper plus. That's not the one I want. I have copper plus going to solid copper. That's also not the one I want. I want copper 2 plus going to solid copper here. Solid copper 2 plus going to solid copper, that's 0.34 volts. That's going to give me a cell potential of 1.10 volts. And that's if both of these are 1 molar concentration. So I'm assuming this is under standard conditions where this would be 1 molar and this would be 1 molar. And since they are the same concentration, the difference in the concentrations isn't going to shift this reaction, right? Because if this is spontaneous, then that reaction is going forward. That's my assumption here, is that my reaction is going forward. But what if my concentration of copper ions was greater than my concentration of zinc ions, then that's going to shift the reaction forward more than I predict. So what that means is that my E cell should be greater than my standard E cell. Because this assumes that there's nothing that's shifting this reaction other than the fact that it's spontaneous. But if I have a difference in concentrations here between these two, now that's going to add an added shift, and it's going to push this reaction forward even more, so my cell potential might be greater than my standard cell potential. And I could calculate that using that Nernst equation. So what I would expect is my E cell would be greater than this. So let's give this some values. Let's say my concentration here was 1.2 molar and my concentration here would be 0.8 molar. So let's see if this is going to hold true. So my Q, my solids fall out. So when I calculate Q is simply going to be zinc ion over copper ion. And so that's 0.8 over 1.2. So my Q is 0.6667. I'm going to plug that into this equation. My N here is 2. When I work through this, I get negative 0.005212. So negative and negative, that's going to end up adding to my standard, and I get 1.11 volts. So not a lot, not a huge change, but it is increasing the cell potential. So oftentimes if I want to create a cell and I want to jump up the cell potential of that, I would just do a concentration gradient, and that would shift that equilibrium a little bit more forward, which would increase the cell potential of that. So I got to find Q first and then relate it back to the cell potential. Now remember a couple of things about Q. We've talked about Q a lot. When Q equals K, I'm at equilibrium. And if Q equals K in this case, then this whole thing would fall out, and these would be equal to each other. So this is only when you're out of equilibrium that Q really has an effect. If Q is less than 1, then your cell is going to be greater than your standard cell potential. So you're going to be driving, that reaction is going to be driven forward toward products more than you would anticipate. If Q is greater than 1, then that means your E cell is going to be less than your standard E cell, and your reaction is going to be driven in reverse. And so you're going to have less of a standard cell potential here. So the one other thing I wanted to cover is these things called concentration cells. So this would be an example of a voltaic cell that's being carried out under non-standard conditions where I have a gradient of concentration. So I have different concentrations here. But I still have a standard cell potential based on ideal conditions. Based on 1 molar and 1 molar, I can calculate this E cell. This is going to generate some electricity. It's going to change if I have a difference in concentrations here, but it's not going to affect it drastically. But we have these things called concentration cells where the difference in concentration is the only thing driving that cell potential. Whereas here, what's driving this cell potential is primarily the redox reaction that's happening. So the difference in concentrations is having a small effect, but it's not the main driver of that cell potential. In a concentration cell, the main driver of that cell potential is the difference in concentrations. So this would be an example of a concentration cell. And what you see here is I have copper ion, solid copper going to copper ion, and copper ion going back to solid copper. And so I don't have a redox reaction. The only thing that's driving this small change in the cell potential is the gradient of the difference in concentrations here. So if I had a 1 molar and a 1 molar, there would be no current that would be happening here because this is at equilibrium. But if I change my concentration slightly between the anode and the cathode, now I'm going to see a change in my cell potential. I'm going to see a small potential here. And that's being driven solely by that difference in concentration. And to find this value, I would plug this into the Nernst equation. My standard E cell would be 0, so the only thing that's driving that is that difference in concentration. So in a concentration cell, you'll find Q, and then you'll multiply that by 0.0592 divided by your number of moles take the opposite sign of that, that's going to give you this. So concentration cells are going to be really small. It's not going to be a great way to generate electrical current because you can see that this is going to be always be a very small value here. All right, we're going to end part 2 here, and we'll come back and talk about batteries in part 3.